Hello. Wait a minute. That is wow. Yes, you're good at wait a minute. Sorry. Oh, am I on mute? Wait. Good. Why? That's fine. Okay. Good afternoon, Gabriella. Good afternoon, Mouse Hat. Good afternoon, and good afternoon, not mask. I might add, that's like the double costume, honestly. But good afternoon, Alyssa. Good afternoon, Vivian. Good afternoon, Jay. Good afternoon, Jayla. I'm assuming Jayla's responding to the mouse hat. I'm not. Anyway, good after. Hi, Michaela. What we agree. Hello, Jayla. Okay, now I wonder what we. Oh, and there's more people. I'm sorry. Hold on, more people coming. Pardon. I wonder what you agreed on. Do we? Oh, and more people coming. Sorry. Hold on. Okay. Good afternoon, Celine. Good afternoon, Andrew. And sorry about yesterday, Andrew, and everybody. But sorry. Good afternoon, Jayla. Good afternoon, Nicholas. Yeah, well, me too. And for reasons that have nothing to do with me at this point, clearly. Okay. She asked you. Well, I'm glad you guys have dialogue about these things. I'm glad that you check in with each other, even if you ignore each other. Okay. Good afternoon, Mark. I I can't from now on, like Mark is indelibly like tied to the I choose independent variable thing in my mind. But now Gabriella is indelibly tied to a mouse, so I don't know what to say. Okay. Just okay, I'm gonna. Oh yeah. All right. Good afternoon, Nicholas. Now gives us. Good afternoon, she. Good afternoon, Catherine. Hi, and good afternoon, Lakshmi. See, she might not have a hat, but she has two greetings. So what's up with that, comma, yo? Good afternoon, Brenda. The okay, Nicholas. What? Oh, now see, one person has a mouse hat, another person has boxing gloves on, named Jayla. Good afternoon, Stephanie. I'm sorry to hear that, Mark. Whoa, and I'm surprised. Anyway, okay, can't beat that. Okay, you guys, you know that. Ding ding. Oh wait, does that mean someone's there? Wait. Or ding ding. Oh, I get it. Boxing. Sorry. Right. Yes, boxing. You know. Okay. Yes, I love this class. One thing I'm gonna miss. What I need a chat in my life. Like, you guys know that I started trying to put a chat on the board, like in physical classrooms now, and you're the only group that has taken advantage of that in your funny way. But I'm serious. I now want to just walk. I'm going to start walking around with a whiteboard on my chest in life and just have it written chat on the top of the whiteboard. Cause like, I need chat in my life. It's all about the chat. Okay, wait. Okay. Can I still? Oh yeah, no, totally, Gabrielle. Make a group chat. But yeah, no. Yeah, no, and I do need to get to business in a minute with you people I mean, there's this thing that I want to do, and I actually want to turn it to you to do for a minute or two in a minute, like a math, physics, like I want to do physics. I know, surprise, weird, I know. But I do want to say again, yes, thank you all for being so flexible and understanding yesterday. Believe me, I was crushed about yesterday too. Believe me, and it's totally not Professor Johnson's fault. I hope that's clear. It's literally a human resources paperwork thing. Like it's just taking so long for them to process the paperwork, which is a really unfortunate snowball effect of like, as though we all weren't suffering enough hiring someone in the middle of the semester, and then it's taking forever, blah, blah, blah. But, and for what it's worth, also the other two physics labs are having a separate issue. So nobody had physics 204 lab this week. We're not going to be missing the material. Like, you're still going to get through the whole curriculum, and you're not going to have to like come in other hours and make it up. Like, it's not on you, it's on me. I hope the free time was at least pleasurable, but no, we will meet Professor Johnson next week, and whatever plans anybody had for that, I hope they maintain them. And we will do the lab next week that we would have done. Well, anyway, that doesn't matter. But so you guys are being very flexible and understanding about it, and I appreciate that, and I love the enthusiasm. And I'm gonna look. Yeah, we tried that. Wait, was it? All right, I shouldn't be laughing, but yeah, A's for everyone. Well, what happened to the 100K, yo? No, just kidding. Okay. Look, and please do remember, I even last semester, and publicly, I cannot promise A's for everyone, but I can promise, and I think I stand by this. I can promise that A's are available to everybody, if you know what I mean. Like, I can at least promise that there's no limit on the A's economics class, and that's not a claim that can be made in all college classes, as we know. And what I mean by that is deserving, legitimate A's are available to anybody who wants them, and frequently people do. But anyway, 10%. Yeah, no, yeah, I shouldn't even make a joke about the subscriber thing, because yes, no, if you guys were, well, okay, I'm not even going to go down that route, but yes, no, I'm still quite moved and quite touched by all that. It was amazing. Yes. And plus, I think some of the people behind that actually did get A's anyway, but whatever. Okay. Okay. I'm going to turn to physics for a moment. Please forgive. I'm going to ask you, I want to get straight back. We're in this differential equation land now. We're actually doing something sort of thick and sort of interesting, and we're finally starting to unpack this harmonic oscillation business, i.e. we're finally starting to get an answer to the last question of the first homework so we can move on with our lives. The way I want to get to it, I want to turn it straight to you. I'll show you what I mean. Oh, whoops, that's not what I mean. Oh, that's me and Professor Walters. Sorry. Yes, if you have any advice, I've never beaten him once, but okay. I want to get totally him. Actually, to be honest, the game right now is unusually tight for us. In fact, even technically, I might be up a piece. It's very, very, very closed, very defensive, very sort of ponderous game right now where it's not clear exactly who's winning. But let me tell you, I never win against him. Like, honestly, he always ends up winning. He's a much better player than I am. The best thing I can do is hold a defensive position for a long time and frustrate the heck out of him. That's like my best game, is just to postpone the inevitable for as long as I can. But he always wins. He's much better than I am. He's really good. And he's really good. Those are not the same statements. But I love playing with him. But anyway, and I miss him. What I want to get to is this. Okay. Okay, that is funny. Yeah, well, it's better than watching golf on TV, I think. Right. Okay. Okay, what's on this page? So I'm going to turn something to you guys in a moment. You're going to do something, believe it or not. I'm not going to make breakout rooms. I don't think it's necessary, but you're certainly welcome to talk to each other with the thing that you're about to do. It's just a little exercise, but here's the deal. Remember, we're trying to solve. Oh, I should cover up. We're trying to solve I'll do it again. We're trying to solve the differential equation on the top here. That's what we're trying to do, right? Again, that thing on the top, that's just Hooke's law, really, written in mathematical form. It's really just saying the acceleration of some system is directly proportional to the position of that system. And we're saying that is a differential equation because we're saying the rate of change of some dependent variable with respect to the independent variable is directly proportional to the dependent variable itself, right? That is an interesting puzzle to try to put together. It's coming up from physics, right? It's literally just a mathematical translation of a physics situation where, well, just what I just said, that the rate of change of position with respect to time is somehow dependent on, in fact, directly proportional to position itself. Now, we want to crack this open. Because what our goal is to be able to predict, given some time, what's the position, right? So that's what we're trying to do. We're trying to get X as a function of T. To be granted, kind of the answers are written right there at the bottom of the page, but don't worry about that for a minute. What I'm going to say is, how do we get the answer, or how do we crack this? How do we solve this differential equation? How do we get X as a function of T? What we do, and what we do is what mathematicians would also do in this case. We conjecture, and then we see if we build a conjecture from experience, from intuition, from from experience and intuition. And then we use rigorous algorithmic procedures to find out if our conjecture is right or wrong, and which we can do, i.e. we ultimately prove whether we are right or wrong. If we find out that our conjecture is right, then we win, and then we have a solution, what is called a solution to the differential equation. If we find out we're wrong, maybe we privately cry, but after we're done crying, we don't like give up or walk away, nor do we throw away our conjecture. We see what was wrong with our conjecture and we tweak it accordingly. So this is what this really is in itself, it's a very experimental kind of way of solving a math problem. It's conjecture and verify or guess and check, but it's also, what's the word? It's also a bit of trial and error. Like we try something and then if it doesn't work, we fix the trial to try to make it work better. It's a very experimental way of solving a math problem. A lot more of math is much more like this than one might guess, or than you might have guessed. Like math is not always a straight line path the way it sometimes seems to be presented. Math itself is much more like science often, particularly when it comes to solving differential equations. Now, what I said yesterday, 2 days ago, is one place where we get our conjecture from, besides our past mathematical experience, is the benefit of being a scientist. We get our conjecture from our lab experience in picturing what lab data would look like. That's what I said on Monday. We get the general shape of our conjecture from lab experience and data collection, the general shape. And then we get the details of that shape, the constants, from scientific considerations such as unit analysis, dimensional analysis. So what I'm going to do here is I'm going to say, okay, and this is, I think, pretty much where we picked up. We're pretty much where left off on Monday. I'm saying on this page, here's my conjecture. And let me be very careful. Okay, here's my conjecture. I mean, and again, please understand, it's a conjecture. It's certainly not true automatically, but it's a thing that I'm going to try. My conjecture is, let's let x equal x naught cosine omega t. Now, first of all, note that has the correct form of the, sorry. That has the correct, please note that has the kind of form that I'm looking for. That is, it has two big ears and a tail in each cheese. No, sorry, that's not what I mean. It has the correct form of what I'm looking for, meaning that it's treating t as the input. It's putting t on the right-hand side, doing a bunch of stuff to t, and then spitting out x on the left-hand side. It is a version of, it's some kind of x as a function of t, which is what we're looking for. We're just trying to find out the right one. Then it has a shape. I've decided, as we said at the end of Monday, I've decided to conjecture that the kind of function that x is of t is a cosine function, because I'm thinking that x goes back and forth in time. So if I plot time on the x-axis and I plot x on the y-axis, I hope that's not too confusing, but if I'm plotting x as the dependent variable and t as the independent variable, then I'm thinking that the graph would look like a cosine. So I'm guessing that the shape is cosine. Then, and here's where, again, where we left off on Monday, I'm saying, okay, like the last thing I said on Monday was, okay, let's guess that our function is some type of cosine function, but we can't literally just guess x equals cosine of t. Like that's too simple. There's no way that's right. At least I know as a scientist, as a physicist, that there's no way that's right. Because as I mentioned Monday, if I think about t and x as actual measurements that are being made in the lab, well, t is measured in seconds and x is measured in meters. So first of all, you can't take the cosine of a second. You just can't. And you have to take the cosine of something like a radian. And second of all, when you take the cosine of something like a radian, what you get out from that is not a radian, nor a second, nor a meter, nor a kilogram. What you get is something dimensionless, like the cosine of 60 degrees, or rather the cosine of pi over 3 radians is, for example, 1/2. my point be not that you have to necessarily memorize that, although you do sort of want to get used to it. But my point is, it's 1/2. The cosine of pi over 3 radians is not 1/2 meters or 1/2 kilograms. It's literally just the number 1/2. So what we decided at the end of Monday is that x has to equal something, like I put a blank space in at the end of notes on Monday, x has to equal something times cosine of something times t. Those blank spaces that I put at the end of Monday, those somethings would be spaces where constants would go, values that I might not know right now. I might write them as letters, right? But they're constants in that for any one given situation, they wouldn't change. For any one given spring and in any one given mass going back and forth, they would represent quantities that would not change. Just like in our whole homework 1 here, like mass is a constant, and K, 200 newtons per meter, is a constant for that spring. It's not the same for every spring. So, I won't build my whole life around that number 200, but it's constant for a given spring. So what I'm saying here is that I'm guessing that x equals some kind of constant times cosine times some type of constant times t, a constant that's not yet known but must be there. So now I'm giving name there. So what I'm doing here, so I left them just as blank spaces on Monday. Again, this is what it means to build up a conjecture. And you're the one class, honestly, this is one class that really, I think, hopefully seeing this theme clearly now. I'm saying really, whether we're in the lab or whether we're in theory land, as physicists, our job is always to do this. We're always trying to build up some model, some relationship, some function that maps one variable to another. And what it means to find that relationship, to derive that equation, whether it's experimentally or theoretically, what it really always means is first have an idea of the shape, the type of relationship, and then have an idea of the details. The details are constants. The shape is a type of function. So the two constants that I think have to be there to make the units work out, one of the constants, you notice on this page, I'm literally, and please take note of this. This tends to confuse people. I'm first of all saying that I'm using this letter that looks like a W. It's actually a lowercase omega. I'm putting it in there for the first time. You might have seen it on the web. You might have seen it in textbooks. But I'm saying it's the first time I'm putting it in the material here in lecture. I'm introducing that omega. I'm not expecting that we have any prior knowledge of it. It doesn't refer to anything that we've said before. What I'm saying right now is it is literally just the name. So I'm choosing to use the omega as the name for this unknown constant that must go before the t if my conjecture is going to work at all. The only thing I know about this omega is the very thing that forces its existence, which is that it must be some kind of number measured in radians per second. Like that's what I'm trying to say in the square brackets there, right? Like I use square brackets to mean units. Okay, so what I'm very much, in fact, I'm even going to say, what I want to make very clear to you all is, like that's a triple equal sign. I'm if I can, I want to be as clear as I can about this. I'm saying right now, and I'll look in the chat in just 1 second. I want to be very clear that I'm saying omega is just a letter that I've chosen. I could have chosen the letter B. I could have chosen the letter C for constant. I'm choosing the letter omega just because all of my physics predecessors before me have chosen it. And it's what we're going to find all over textbooks and web. So we want to communicate with the rest of the world, blah, 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 blah. But I'm just choosing this letter as a name to stand for some unknown constant that I believe must be there and must be measured in radians per second. In other words, all I know about omega at this moment is that it's some number measured in radians per second. And I'm calling it omega because I feel like it, because I have to call it something. Like, okay, honestly. So I'm just saying, let's imagine there's some letter there. I mean, there's some number there. I don't know what it is yet. Maybe it'll differ from spring to spring, but it'll stay steady with the spring. And whatever that number is, it's going to be measured in radians per second. And I will look in the chat in a sec. So I'm introduced. So omega right now is just some number measured in radians per second. Then I'm the constant that's going before the cosine. It has to be something that's measured in meters. I could have called that some other Greek letter if I wanted. I could have called that theta, or no, not theta. I mean, I could have called it tau or something, or I could have called it an English letter like B. But then I realized, wait a second, you know what? Actually, the letter that's going, the unknown constant that's going before the cosine, that must be measured in meters. And again, why must it be? Because cosine spits out a dimensionless output, but the whole answer, x, has to be a displacement measured in meters. So cosine spits out something, and it's going to have to be multiplied by some number measured in meters. And then it occurred to me, like, wait a second, one thing I do know if I'm guessing cosine here, and all this is just me building up my guess, this is just me constructing the most educated guess I can. But I'm guessing cosine, and I do know certain things about cosine. Like, for example, I know that the sine of 0 is 0 and the cosine of 0 is 1. Like, and that's something you want to get used to and sort of maybe commit to memory. Like, I think most people know that sine and cosine are very related, and everybody sort of knows they're kind of the same thing, but they're like backwards of each other. And everybody kind of knows if they know the sine of one thing, then cosine is the other one of that. But then everybody gets them all confused. And I will shut up in a second and check the chat. But just one little handy thing, if you're sort of in that realm where you sort of get what's going on with sine and cosine, but you sort of get them confused or whatever, just please, for all time, if you're going to remember one thing to anchor all your other memories, for all time, just remember sine of 0, 0. It's like a snake. It's just like a bunch of S's. Sine of 0 is 0. And then from that, then if sine of 0 is 0, then cosine of 0 is not. It's the other thing. It's 1. Put it one better way. The way I actually remember what I actually remember is sine is super, cosine is crappy. Or put another way, sine is super, cosine is crazy. Or put another way, sine is super, cosine is counterintuitive. By which I mean, if you're ever trying to like get them straight or whatever, sine is the function that does what you would have it do. If you were inventing all this crap on your own on a desert island, the sine of 0 is 0. And then as the angle gets bigger, the sine gets bigger. It's like exactly what we'd all want any good, well-behaved function to do. As the input gets bigger, the output gets bigger. When the input is nothing, the output is nothing. It's just like at the beginning. Sine is that thing. Cosine is the one that's backwards. Cosine is the one that cosine of 0 is 1. When the angle is nothing, cosine starts off with this maximum value. And then as the angle gets bigger, cosine gets smaller. It all makes sense if you picture the unit circle, but if you're not as good friends with the unit circle as I happen to be, like some of my best friends are the unit circle, if you don't love the unit circle, just remember sine super, cosine counterintuitive. Okay, now why am I saying all that? Because I'm ignoring the chat. I know, I mean, I don't mean to be, but I've got to finish my thought before I die. Cosine of 0 is 1. Cosine of 0 is 1. So when t is 0, that whole cosine thing is going to turn to 1, right? When t is 0, that whole cosine expression is going to turn to 1. But we know when t is 0, x is supposed to be whatever x is initially when t is 0. X is supposed to be its very first value when t is 0. Like in the case of this homework 1, when t is 0, x is 0.15 meters. We call that x naught. The initial value of x, the value of x when t is 0. So in fact, if you think about it, it's x naught. X naught is something that's measured in meters. And it is in fact the thing that I believe we should multiply the whole cosine by, so that in other words, if we didn't have x naught there, cosine, as you know, would fluctuate back and forth between -1 all the way to 1 to -1 to 1, right? Like cosine of an angle never gets greater than 1 and never gets less than -1. So all of our outputs would always just be somewhere between 1 and -1. but we're in reality here. We've got a spring. We're not it's not a rule that the spring had to start at 1 meter on the right-hand side and just oscillate back and forth between 1 meter on the right-hand side and -1 meter on the other. In our case, it's oscillating back and forth between 0.15 meters and -0.15. So if you think about it, like wherever it started is kind of like just a scaling factor on the cosine function. It's just adapting the cosine function to whatever in reality is happening on the meter stick. So I'm saying right now, and I'm talking a lot, I'm going to check the chat, then I'm going to turn it to you. I'm saying right now I have a conjecture that the function I think that's going to solve my differential equation is x naught times cosine times something measured in radians per second times t. That's my conjecture. And the thing that's measured in radians per second, I'm going to call omega. That's my mathematical conjecture, is that x equals x naught cosine omega t might well be a solution to the differential equation d2x dt squared equals negative k over m x. That's my conjecture. We're going to test in a minute. In fact, you're going to test in a minute. But first, something's been happening in the chat that, oh, right. Wait, what? Oh my God. Wait, so Gabrielle knows about the 100K thing? Because we could use some help here, people, Gabrielle. Like, where are you on the 100K thing? But okay. That's so inappropriate on my part. I can't even believe it. All right. You know what? It's really hard. I often feel like I'm being inappropriate, and then I want to fire myself. And then I remember I have tenure, so then like I get into a whole personal conflict. Okay. So what are we gonna do? We're gonna do this. You are gonna take a couple of minutes. Some of you, this is going to take 1 second. Some of you might have already done it. Yeah, there we go. Come on. All right. Now we're talking. Nicholas and Gabrielle will have a private meeting afterwards to discuss what. Okay. What you're guys going to do now is you're going to check. You're going to check if our conjecture is right. What does it mean to check if it's right? We're going to find out. Remember, we're trying to guess a function whose second derivative with respect to time does a certain thing. Does what? Does equal negative times some constant times itself. Our whole question is, can we find an x such that d2x dt squared equals negative k over m times x? So we have a conjecture now. I'm going to turn it to you guys. Take a couple. I want you to take the x that we're conjecturing, this x right here, this x function, and take the derivative of it with respect to time. Take the dx dt, like pretend it's a calculus class. Recognize that x naught and omega are constants. They're just like numbers. If they bother you, you can turn them into numbers and then turn them back at the end. X is a variable, t is the independent variable. I want, please, everybody to take a moment and maybe, and I'm even going to say this, please put in the private chat, so that you don't mess with it. In the private chat, once you think you have an answer to dx dt and then an answer, a second answer to d2x dt squared, please put that in the private chat, or in the private chat say, I don't know what's going on, or I'm stuck here, or could you repeat the question, or just like, let's be in the private chat for a couple minutes. So everybody try this, please. I want you to take the function that we conjectured on page 2 and take 2 derivatives of it. Take a derivative and then take a derivative again and see what you get. You should get some kind of function with a bunch of x's and t's and letters in it. But okay, and I'm just looking at this. So please try. Like this is a do now. And forgive me if I might turn my video and mute off for a moment, but please send me the things in direct chat. I'm going to pause for a second myself. And if you don't know what I'm asking you, please tell me that in the direct chat. But I'm assuming everybody knows, I assume everybody gets the instruction. So I'm going to black box myself for a second. I'm looking at, sorry, keep working every day. I'm trying to catch up in the chat. So bear with me, but just keep working. And if you're done, if you, well, if you're done, I'm going to try to catch up in the chat. But if you already flew through and you feel like you know what's going on, I would suggest go back to the first page of the notes and see if you understand what's happening with the third line on that page, if you're already there. But let me catch up with the chat. I apologize. Hold on. Oh, wow, there's a lot. I'm very impressed. Hold on. Wait. So again, I'm just. Oh, great. Oh, these are great questions. Bear with me. These are great questions in the chat. I really appreciate this. And again, so if you think you're already done, also you can get a cup of coffee or whatever, but yeah, these are great questions. I will try to answer. I want to answer these first in the chat. And by the way, all of you who put anything in the chat, also, you could also take a moment to look at the participation, the game portals. Like there's different ways that some of you can submit for credit right now in the game portals. Like if you put something in the chat at all, you can definitely submit it to that game portal that's called For Right or For Wrong. Maybe some of you know what I'm talking about, and maybe some of you don't, but any game portal that just flip through them and see anyone that applies to how you're participating right now and just submit for points. If that makes, and if you don't know what I'm saying, then when I'm done with this, please ask me and I'll explain to the whole class. But all of you who are participating in the chat right now should get points for this. So if you're like needing something to do right now, that's something you could do. But because I love these questions, so I want to take them seriously. And I know that some of you are asking questions in a private chat that you would never ask in public. So I do want to honor them. Okay, I think. So, so, oh, oh, wait. Oh, there's more. Oh, there's more that I missed. I'm sorry. How did I miss all this? There's a lot in the chat. I'm sorry. Hang on. Somehow I missed. Ah, oh, okay. I knew I missed. Oh, I'm, I know there's still one more person. I keep losing. This chat needs to be. Oh, Okay, I think I'm in. Ah, okay, I think. Okay, I think. Forgive me. I think I've now seen and replied to everything in the chat. And boy, so I'm gonna start talking again. Forgive me, please. Let me see if that. I have to tell you, like I know that's it's all a very sort of inefficient process, the me doing the private, but I've got it. I'm gonna go over these obviously, but I very much appreciate what just happened in the chat. Like I feel like, granted, that was not a group conversation, that was a lot of individual conversations, but boy, do I feel much more clear on where you all are with this. And for what it's worth to all of you, there was a lot of you are not entirely sure of this. Okay. If you're feeling not entirely sure of the answer or what I'm asking as a question, you are not alone. You are not alone. And that is not a criticism. I want to make it clear. Like, this is why sometimes the direct chat thing is a very cool thing. Like, honestly, I think a lot of you are having a little bit of an issue with this, which is just good. That, first of all, that means that now if I teach it, I'm not wasting your time and I'm not boring you, right? Like, it was good for me to know that. And second of all, if you're a little worried that you don't get what's going on, please know that's true of other people. So now also please pay attention to court, like when I now explain it. But I think this was good. And I really appreciate the guts or the honesty that everybody showed by putting where they were in the chat. If you didn't put anything at all, I mean, I hope that's just because like you're too nervous, not because you've totally given up or spaced out or whatever. I'm gonna guess that if you didn't put anything in at all, it's not because you think it's such a. I'm guessing that anybody who didn't put anything at all, it wasn't because they just think this is a joke and it's so obviously easy. Like it doesn't seem like anybody just thinks it's an obvious, easy joke waste of time. Right? Because if it were that, that doesn't seem that way. So I'm just saying that again as a way of like, please, when we have these opportunities, please don't be shy about putting stuff in. Like I can teach you much better if I know where you're at. There's like an old joke about that. Like if someone calls me on the phone, if I call you on the phone and I'm like, oh my God, like class, I'm lost. Like I'm in my car and I'm totally lost. Can you please tell me how to get to John Jay? What's the first thing you're going to say to me? If I'm just like, well, thank you. I totally appreciate it. All right. And if you would, I appreciate it. Let's say literally, I mean, this is like stupid on my part, but let's just get this straight. If I called any of you or all of you and I'm like barking into the phone or I'm nice in the phone, but I'm just like, I'm totally lost. I'm totally lost. I'm totally lost. I'm totally lost. Like, how do I get to John Jay? What's the first thing you're going to ask me? And I'm actually asking you to tell me in the chat, one of you. What? Well, okay. Fair enough. God dang it. Yes. All right. Fair enough. But like, if it weren't, all right, I can't do anything with it. Right. Thank you, Rishi. Yes. Woo! Yes, exactly. You'd say, where are you? And like, of course, then I might be like, well, if I knew, I wouldn't be lost. But like, I would be like, oh, I'm outside a gas station. There's a neon sign. It says, oh, yeah, whatever, right? Like, the only way you can help me get to where you need me to be is if you know where I am right now. And that's it. You get my analogy, right? So I'm glad that a lot of people participate in the chat. I now know that I do need to explain this. It does seem pretty apparent that I do need to, and I will. But let me also please remind you, a lot happened in that chat there. Please look, a lot of people should get a lot of points. You can double dip and triple dip into any game portal that applies to what you just did. And for example, want to remind you, because it means a lot to me, and I think it's a very important scientific and human skill. Some of you put something in the chat, like there was like a question or like, I have no idea what to do or whatever. And then I told you something, I gave you some hint or some suggestion. And then some of you, after I wrote the suggestion, wrote back something like, okay, got it, thanks, or something like, and I don't know if you really got it. I don't know what you did next, but you like acknowledged my acknowledgement, right? That is what I consider closing a conversational path. If you like actually show that if you close the loop, right? It's almost like putting a freaking tap back in texting, which by the way, I think is the best invention of this decade. Like, the little thumb, I think they're called tap backs, but like, if you ask me a question, I give you an answer, then you're like, I got the answer. Thank you. I confirm receipt. I think that's a really important thing to do, especially in these crazy remote classes and all that. But as a scientist, to like, so there is a portal for that. If you even literally just said, thank you, got it, so I don't feel crazy or like I'm talking to it, you can submit that for points. All right, yes, that is also true. But all right, and if you don't, then you don't get the points. But the other thing, please note, for those of you who don't, there's at least one portal that's called like be wrong, be really, really wrong. If you said anything in the chat that then was concrete and gutsy enough that it prompted me to be like, okay, but no, like you forgot chain rule or something, if I correct, put that in for points. If you actually were wrong about something, wrong enough for me to say that's wrong or that's incomplete, or you need to do like, good on both of us. Like, you should get points for that. So please, all of you, like, I think it was a good discussion. Okay, so now I'm going to do it. Okay. What I'm at, oh, and let me just look in the chat what I just missed. Hold on a second. Right. Oh, and I'm so sorry. Oh, my bad too. Like when I said that map analogy thing, and she's answer like popped up on my screen, but I didn't see that Mark had also answered and Stephanie had also answered and she had answered. So thank you. That's totally points. I apologize. I totally did not see that. I'm seeing it now. See, now I'm closing the, see, it's like, I see you, you know what I'm saying? Okay. So I see Mark and I see Stephanie, and I apologize that I didn't see them at the crucial moment of hour of need. Okay. Now what I'm doing, what I'm asking is to take some derivatives now. Now, many of you in the chat said things like, I kind of get what's going on, but I don't, like, are there numbers? Like, what am I don't, like, I know what a derivative is, but I don't know what is it that you want me to take the derivative of. Okay, so I'll show you what, so I'm just going to go there. What the function that we're taking the derivative of. Now, that may look very confusing. At least one, it looks like it has a lot of variables in it. At least one person did this very clever, impressive thing of trying to do a product rule. Because at least one, maybe it was two people, thought like, oh, we've got like a product of two functions, x naught and cosine omega t. Very, very clever. But this isn't even that hard, as hard as that actually, because there's well, so what this is really like, if we're pretending this is a calculus class, what this is like, it's like, and okay, the question for me, the physics question is, I said, I asked you all to compute dx dt to get the derivative of x with respect to t. Now, let me show you what this is as though we were in a calculus class. This is as though This is as though I had written the function y equals 5 cosine 3x, and I'm asking for dy dx. Okay, 5 and 3 are arbitrary. I just made up those numbers, but that's the point. Like x naught is just some number. It's a letter, but it stands for some number that, although we don't know it, it's not going to change. Hence, we call it a constant. Same thing with the omega, is just some number. So I'm pretending it's 3 right now. Okay. So part of what's confusing to some of you is that there's like all these letters here and you don't like know which one is doing what. Another thing that's confusing to some of you is you're used to in calculus class, you're used to functions looking like y as a function of x, and then you're used to getting dy dx. I'm trying to break us out of those rigid boxes, and I'm trying to say it never really mattered whether we called it y or we called it x, and it never really mattered whether the number was 5 or 3 or we called it m, as in y equals mx plus b. The important thing always in calculus is that we were dealing with functions, and functions involve independent variables, dependent variables, and constants. So I'm going to pretend this were a calculus class, and I'd said, here's the function y equals 5 cosine of 3x. I'm asking, what is dy of dx? In fact, I'm going to go a step even more. Let's pretend this, just pretend. And now here, I know we only have 15 minutes, so I'm going to say now, right now, I'm opening this up. I'm going to ask a series of questions and open it up to public chat now. Like, I don't want to get all bogged down, but please feel free. If you feel like you have an answer or a thought about anything, I'm trying to break the question down to see where we're at. So please use the public chat if you dare. Like, say I said, if I said y equals cosine of x, and then asked for dy dx, what would the answer be? If this were a math class, if I just said y equals cosine of x, what is dy dx? Like, what's the derivative of y with respect to x? If I said y equals cosine of it. Yes, that was fast. Oh, look how fast you guys are. That's awesome. And that tells me a lot too. Great, great Celine, great Catherine, great Stephanie. Awesome. I totally agree. Right, is that right? And granted, this is a thing for math class. Like, I'm not even really right now pretending fully to explain it, but it is true that the derivative of cosine is negative sine. The derivative of sine is cosine. So if I had asked, so I agree. If I had said, now similarly, if I had said, what if I had said this, x equals cosine of t, and then I had asked, what's dx dt? The answer to that would be, like, in other words, if I just change the letters around, then I'm just going to change the letters around accordingly. If I gave you x equals cosine of t, which is a more physical kind of, that, right, thank you, that was fast. Oh, look how fast that is. Thank you, Ishi. Thank you, Catherine. Thank you, Celine. Yeah, you would get that, right? Awesome. Now I'm going to take it a step further. What if I had said, y equals 5 cosine x? What would dy dx equal? Yes, totally, Celine, right? Like, the constant just gets carried along for the ride. Now, look, and I know that there are still some of you in the room who are still like, well, great, thank you, Yaverbaum. Like, you're just asking the same question with different letters, but I didn't know it then, so I still don't know it now. There still may be some of you that this is not helping, and if it's not helping, if you're still confused, at least make a mental note of that. Know that you should not be ashamed. I'm serious. If you're still confused by what's going on, this might or might not be the time to say it. I can understand why you wouldn't want to say it publicly. Maybe you don't even want to say it privately right now because, like, I'm like starting to move fast, but just make a mental note of it and know that if you ask me later, if any one of you has the guts to later on say, I still didn't follow that stuff about 5 cosine x, just let me know at some point somehow, or text me on the phone. There's no shame. I don't expect that you all love or have mastered calculus. What I expect is that we could, if we still haven't fully given up. Okay, so just don't give up, and don't assume that I'm going to chastise you if you're not there yet. I'm not. You might be making good judgment to keep it to yourself right now, so I can go on. But please just make a mental note. If you still don't know what's going on, make a mental note, and we'll talk about it. But okay, but now I'm going to go back to this. And I'm going to say, okay, so I'm going to take it another step further. Say I said, let x equal m cosine of t, where m is some letter, like it's a constant, as in y equals mx plus b. If I said that x equals m cosine t, then what's dx dt? If so in other words, instead of the number 5, I'm just calling it the number m. Yeah, right. Thank you, Celine. Exactly. And I know, and again, by the way, if this were the beginning, and thank you, Stephanie. And I was just going to say, even if someone's already put in the chat, don't feel like anybody still can't. And remember, if nothing else, you really can submit these for points. And yes, I'm starting to move a little faster now because we only have 11 minutes. But even if something hits you 5 minutes from now, put it in the chat. Like, okay, like I'm not trying to rush you. I'm just trying to rush me. So yes, if x equals m cosine omega t, then dx dt would equal negative m sine t, right? I'm just trying to, and so for we're almost at the example on hand. What we're now saying is if, let's say, if x equaled x naught cos omega t. Now, it's still not quite what we have. But one thing is, notice, like, part of what confuses this about people, like what I'm trying to say is x naught is just a name for a constant. Just like m is the name for a constant, just like the number 5 is a constant. But it's very easy not to see that. Like once I say it, hopefully it's clear to some of you. But I totally understand where if you just see this function written at the top of the page at the beginning, x and x naught both look like variables. I mean, let me be clear about this. X naught is the initial value of the variable x. X is like, where is the thing? And at every single moment that changes. X naught is our permanent record of where was the thing at t equals 0. So x naught is actually a constant, even though it has the letter x in it. Do you see? And again, if you sort of never got that before, don't be ashamed of yourself. You might not have known that you didn't get that until right now. That is fine. Like, but get it, right? So I'm saying if x naught is just a constant, then dx dt will equal, if anybody, so if x equals, so we're almost at the function we had, but if we now have x equals x naught times cosine of t, then dx dt would equal, if anybody wants to put in the chat, awesome, yes, yes, oh, that was like 3 people, thank you, Celine, thank you, Catherine, which is a new person, which is great, thank you, Stephanie, yes, yes, totally, totally, right? So, and you know, you might say it's x naught times, like you might see it more easily this way. Yeah, you might see. Like you might think of it that way, but then I just brought out the negative sign to just make it more clean or whatever. But yes, now, so what we're doing right now is taking a trigonometric derivative. The one thing in all this that sort of required a memorizer is, yes, I'm assuming that somewhere in my back of my mind from, as someone said, well, I know we all took calculus a minute ago. So maybe you didn't initially remember, but maybe somewhere in your mind, you remember that the derivative of sine is cosine. The derivative of cosine is negative sine. I'll even try to explain that again to people maybe next class, but that is a thing, yes. And that thing is sort of all we're using here so far. We're just in our mind knowing that t is the variable and everything else is a constant. But then the one piece that makes it a little bit more complicated, we have we have one more constant in our expression, not just that x naught constant, but this omega constant. And again, what I'm trying to encourage you to realize is, in order to take derivatives or do this stuff, you don't need to know anything specific about omega. It doesn't even matter that it's in radians per second. You don't even have to remember why I put it in the first place, but it's there. It's a constant. The one thing you have to realize, though, when we do this is now what we have we still only have one variable. So we don't have to use product rule or quotient rule, or like we don't have the product of two functions or anything like that. But what we do have now strictly speaking, our expression is a function of a function, right? It's like take t, t is a variable, multiply it by omega. So our first function is like omega times t. And then take the cosine multiplied by x naught of that. So it's like stick t into the omega box, then stick that, like, and then out it comes as output, then make that the input in the next box called cosine, right? What we really have is a function of a function now here. So this actually does require chain rule. What? I'm just looking at the time. Yeah. Now, I know I have 5 minutes. Here's my quick, I'm saying we have to do the chain rule. You might be like, oh, great. I thought this wasn't going to be, are you kidding? Chain rule now? But look, here's my quick way to understand and apply the chain rule. This is how I think of the chain rule. The chain rule applies whenever you have a function of a function, like where y is some function of x, but then y is being plugged into some other function, call it g, and spitting out z, right? If you have a function of a function, then what chain rule says is, well, then the derivative of z with respect to, like, look at my bottom line here, dz dx, like the derivative of the outermost thing with respect to the innermost thing equals the derivative of the outer times the derivative of the inner, right? It actually makes sense when you write it like this. When you write it the way I just wrote it, to me, it kind of makes sense. The chain rule is saying if you have a function of a function, but you want the derivative of the whole thing, then it's the derivative of the outside times the derivative of the inside. Therefore, in this case, what does that mean? Well, in this case, like the derivative, so say z equals omega t. If I were in a calculus class right now, we're going to do this very quickly, 4 minutes. If I just walked in and said z equals omega times t, and omega is a constant, it's like saying z equals m times t. If I say what's dz dt, what's the derivative of that? If t is the variable and omega is the constant, what is the answer to what's on the board right here? Yes. That was fast. Yes, that's awesome. And I was actually a little worried for a minute because I think it's yes, Celine, and yes, Catherine. Like the derivative would be omega. So what's my point? My point is that the derivative of the inside, the derivative of that function inside the parentheses is omega. The derivative of the whole outside is the negative sign thing. So our final answer is going to be 1 multiplied by the other. I'm saying this a little bit quickly because I know we have 3 minutes. So I'm saying thus, with 3 minutes left or 2 minutes left, I'm saying then that if you just break down our function and make it look more like from a math class, like you realize it could have been y's and x's instead of x's and t's, and you realize that the constants are just like numbers, then what we get using trigonometric derivatives and chain rule is that the derivative of our function, the first derivative is negative x naught omega times sine of omega t. That's the derivative. Now I have 1 minute left. We'll pick up on this next Monday. And again, be honest with yourself and then honest with me about where you are with this, because we do need this, but I'll take as long as we need to do it. It's like an important life skill. Maybe not life skill, but then therefore with the 1 minute left, I'm going to tell you, if this makes sense, I'm going to get what we were looking for. I'm going to get the second derivative of this. I'm going to take the derivative again. If dx, I'm just recopying it really quick. If dx dt equals negative x naught omega sine of omega t, right? You can put brackets on this if you like, you don't have to. Then take the derivative again. I'm just going to do literally the same thing again. I'm going to say the derivative of negative sine is the derivative of sine is cosine. So the negative signs don't go away. The x naught stays there for the ride, and omega comes out again. Like I have to do chain rule again. So I'm going a little fast now, but look at it in your own private Idaho. D2x dt squared equals negative x naught omega squared cosine omega t. Now we have 1 minute left. Check this out. I'm just rearranging to make it look nicer. I'm just rearranging the constants. So I say this. I'm saying the second derivative of x with respect to t equals negative omega squared times x naught times cosine omega t. So what does that show? What does that prove? Well, notice this whole thing here was x, right? We conjectured that x equaled x naught cosine omega t. Thus, apparently, if we guess that x, then the second derivative of x does equal negative sine times a constant, like omega is just a constant, so omega squared is just a constant, times x. We did pick a function whose second derivative is directly proportional to itself. I will start with this on Monday, but let me say, even if this went a little faster, we actually did just prove that our conjecture is right. Because when we picked an x, that when we took two derivatives of it, we got back itself times some kind of constant times a negative sign. That's what we were looking for. This, as long as this omega squared is just another name for k over m, then we've solved it. And we have found that x equals x naught times cosine omega t, for which omega is the square root of k over m, like it says on the front page of the whole notes. But that you might want to let that sink in or think about it, but that's it. You guys have been very awesome, very patient, and I can't wait to laugh. Yes, Squank. Oh my God, I will have a cheesy day. Yes, Squank, you're very welcome, house. Yes, thank you guys. Thank you very much. Awesome. I can't wait to see you next week. Yes, have a great. Yes, have a great. Yes, thank you, guys. Awesome. Have a good afternoon. You too. Day. Yes. God. Awesome. Thank you. Have a great day. Yes. Have a great week. In fact, I'll see you on the other side of 100. Okay.